Hi friends, this is Naresh. This is my 8th lecture on mechanics of solids or strength of materials subject. This is common for second year B.Tech and second year diploma mechanical students. Okay. In this session, I am going to explain about bars of varying cross sections. Okay. Bars of varying cross sections. A bar of different lengths of different diameters and hence of different cross section areas is shown in figure. Let this bar is subjected to an axial pull load T. Uh, through each section is subjected to the same axial load P, yet the stresses, strains and change in length will be different. The total change in length will be obtained by adding the changes in lengths of individual sections. Okay. So here you can observe here this is a cross section, different cross sections. Here this one is a smaller diameter, so this having a different cross section area, and this one also having a different diameter, so it is cross sectional area 2, and this one also a cross different than these two, so this one is the another cross sectional area A3. Okay, this is the sectional view. Okay, this is the sectional view of this figure. Okay, this is a three-dimensional view, that is isometric view. Okay, this is our schematic view. Okay, by using this diagram you have to find out the stresses induced in each length, and also you have to find the stresses and strains induced in these three bars. Okay, here the load acting on each bar is same. Okay, in this figure the load acting on each bar is equal to P1 or P. Okay, but the cross sectional areas are different. Okay, here the diameter D1, here the diameter D1 is given, that means the area A1 equal to pi by 4 D1 square. Okay, here the diameter D2 is given, that is area 2 equal to pi by 4 D2 square. Okay, and here the diameter of this bar equal to D3, so the cross section area A3 for this bar equal to A3 equal to pi by 4 D3 square. Okay, the length, these are the original lengths. L1 is the original length of the bar 1, L2 is the original length of the bar 2, L3 is the original length of the bar 3. Okay, by using these original lengths you have to find out the delta change in lengths, that is delta L1, delta L2, delta L3. Okay, yeah, P is the load, axial load acting on the bar. It may axial pull or push load. Okay, depends upon our problem. L1 is the length of the section 1, L2 is A1 is the area of the section 1, and L2 is the length of the section 2, and A2 is the area of the section 2 or area of the bar. L3 is the length of the third bar, and A3 is the cross section area of the bar. Okay, Young's modulus, this capital E is the Young's modulus for this material. Okay. So by using this formula, first of all you have to find out the stress and strains. Okay, already we know the formula for stress. The formula for stress equal to load by cross section area. So for the stress induced in the bar 1 is obtained from the formula sigma 1 is the stress induced in the bar 1. So load acting on the bar divided by cross sectional area of the bar A1. So P by A1, the load acting on bar 1, bar 2, bar 3, these the load acting on each bar is same. So P is the P1, P2, P3 is equal to P. Okay, so the load acting on bar 1 equal to P by cross section area of the bar 1 equal to A1. So P by A1 is the stress induced in the bar 1. Similarly, sigma 2 equal to stress induced in the bar 2. Okay, the formula for sigma 2 equal to P by A2. So P is the load acting on the bar 2 and A2 is the area of the bar 2. Similarly, A3 sigma 3 is the stress induced in the bar 3. Okay, the formula for sigma 3 equal to P by A3. Okay, P equal to load acting on the bar 3 and A3 is the cross section area of the bar 3. Okay, so by using by using Young's modulus formula, already we know the formula for Young's modulus. Young's modulus equal to, yeah, already we know that the Young's modulus equal to stress by strain. Okay, so the formula for Young's modulus equal to stress by strain. So by using this strain formula, we need to calculate a change in length. Uh, so we need a formula for strain. So the formula for strain equal to delta L by L. Okay, delta L by L or sigma by capital E. Sigma by capital E. So this is the formula for strain. This one also equal to delta L by L. Okay, strain. This is the strain. This is the formula for strain. Strain E equal to sigma by E or delta L by L. Okay, and also another formula is there, that is sigma equal to P by A by E. This is also another formula. Okay, so by using these three formulas, you have to find out the strain induced in each bar. Okay, so strain sigma 1 induced in the section 1 or induced in bar 1 equal to sigma 1 by E. Okay, sigma 1 by E equal to P by A1 E. Okay, the formula for sigma 1 equal to P by A1. So you have to substitute the value of sigma 1. Okay, so this is the formula for sigma 1. Similarly, for strain induced in bar 2 equal to sigma 2 by E, and similarly the strain induced in the bar 3 equal to sigma 3 by E. Okay, these are the formulas for strains. These three are the formulas for stress. These three are the formulas for strain. Okay, so this sigma 1, sigma 2, sigma 3, these three formulas are used for determining stresses induced in each bar. Okay, and epsilon 1, epsilon 2, epsilon 3, these three formulas are used for determining the strain induced in the each bar. Okay, and now if we want to determine the value of change in length in each bar, then by using this strain formula, okay, strain equal to delta L by L. Okay, from these equations we will get the answers E1, epsilon 1, epsilon 2, epsilon 3, that is strain values. By substituting those values in this equation, you will get the value of delta L1. Okay, so this is the formula for change in the formula obtained from here. You can see the formula for change in length. The formula for change in length equal to, here, this is the formula for change in length, delta L1 equal to epsilon 1 into L1. Okay, so epsilon 1 is the strain. You have to substitute the formula for strain. See, epsilon 1 equal to P by A1 E. Okay, P by A1 E is the formula for epsilon 1, that is strain, and L1 is the original length. So this is the formula for delta L1, that is change in length. Okay, this is the formula for change in length in bar 1. Okay, similarly, this is the formula for change in length in bar 2, that is delta L2. Delta L2 is the formula for change in length in bar 2. Okay, and similarly the formula for change in length in bar 3 equal to DL3 equal to PL3 by A3 into E. So these are the three formulas for change in length or deformation. change in length or deformation in the bar. Okay. So then after you have to find out the total change in length. If you want to find out the total change in length, then use by using this formula you will get the answer for change in length, total change in length. Okay, this is the formula for total deformation. Total deformation in the bar, in the bar. Okay, so this is the formula for total change in length. That is delta L equal to delta L1 plus delta L2 plus delta L3. You have to consider positive sign for tensile loads and negative sign for compressive loads. Okay, so here this is the final formula for change total change in length. Delta L equal to, if you know the here here capital E is the Young's modulus for this material. If the each bar having different materials, then you have to consider different Young's modulus. Okay, E1, E2, E3 are the separate values for separate materials. Okay, if each bar is made up of same material, then you can consider same E value. Okay, so this is the final formula. This final formula for total deformation in the bar. Okay, here one note is there. There is a, you have to consider positive sign. Here plus plus is there. Positive sign for tensile loads. Tensile or pull loads. Okay, you have to consider positive sign for tensile loads and a negative sign for compressive loads. Compressive or push loads. Okay, this is very important in our problems. Positive sign for tensile loads, negative sign for compressive loads. Okay, so I'm going to explain same concept in another way. So here, this is a diagram. This is also a bar of varying cross sections diagram. Okay, and this one also another example for bars of varying cross sections. And this one is the flow diagram for this diagram for this step shaft. Okay, how to determine the total change in length, total change in length or total deformation in the composite bar? I will explain here. Yeah, this is the this is the example for compressive loads. Okay, this is the example for tensile loads. Here, these two are the equal and opposite pull loads. That means tensile loads. Here, the tensile loads are acting on this bar. Same diagram, but here the load acting on in downward direction. That means it pushes the composite figure. So then compressive loads are acting on the bar. So for this loads you have to consider negative sign for compression, and for this diagram for this loads you have to consider positive sign for tension, because here when you are applying tensile loads, then the bar may extend. Okay, so that's why you have to consider positive sign. Here, in case of compressive loads, when you are applying compressive loads, the bar may compress. That means it may reduce the shape. So that's why you have to consider negative sign for compressed loads, positive sign for tensile loads. Okay, same concept. Okay, P is the load acting on the bar, M smallest of the bar, E is the M smallest, L1, L2, L3 are the lengths of the bar, and A1, A2, A3 are the areas of the cross sections. Okay, yeah, the formula for stress equal to load by cross section area, stress in bar 1 equal to sigma equal to P by A1. This is formula. If different loads are acting on the bar, then you have to consider different different loads for stresses. Here the same load acting on the each bar. So here P1 equal to P2 equal to P3 equal to P. Okay, here P1 equal to P2 equal to P3. P3 equal to P. Okay, this is the formula for this is the load acting on each bar. Okay, so here this is the formula for stress induced in each bar. Okay, and from Young's modulus formula, Young's modulus equals stress by strain. There is a load by there is stress by strain. Young's modulus equals stress by strain. So stress equal to load by area, strain equal to delta L by L, change in length by origin length. So by using this formula, uh, we have to find out the formula for delta L, that is change in length. Delta L equal to PL by AE is the formula for change in length. Okay, so delta L1 is the formula for delta L1 equal to PL1 by A1 E is the formula for change in length in bar 1, and this is the formula for change in length for bar 2, and so on. This is the formula for total deformation of the bar. Total deformation is obtained from the summation of individual deformations. So delta L1, delta L2, delta L3, and so on. These are the individual deformations or individual change in lengths. Okay, by adding all these values, you will get the final total deformation value. Okay, so here the load acting on each bar is same. If the load acting on each bar is same, then you can consider P1 equal P2 equal P3 equal P, and also similarly E is the Young's modulus. If each bar is made up of same material, then you have to consider Young's modulus is 1, is same. Okay, so this is the final formula for change in length, and also this is the another formula. Okay, sometimes the modulus of elasticity is different for different sections. In such cases, the total deformation equal to P of L1 by A1 E plus L2 by A2 E plus L3 by A3 E. So this one and this one is both are same. Okay, so this is the formulas. These are the formulas used in our problems. Okay, now I am going to explain about some examples on these formulas. First example, an automobile component shown in figure is subjected to a tensile load of 160 kilonewtons. Determine the total elongation of the component if its modulus of elasticity is 200 GPa. Okay, this is the problem. So here the automobile component is given. So here the load acting on the bar is given, that is a 160 kilonewton, that is P, load P. Okay, this is the load acting on the each bar, that is P equal to 160 kilonewtons. Yeah, this is also P. This one also P. Okay, here, so the load acting on this small bar and this bigger bar is same. So that is P1 equal to P2 equal to P. Determine the total elongation of the component. That is total elongation means delta L. Okay, total elongation means delta L. Total deformation or total change in length or total extension is same. So delta L equal to, we have to find the value of delta L, and here the modulus of elasticity or Young's modulus. This is modulus of elasticity, also known as Young's modulus. So Young's modulus, the value of Young's modulus is given, that is capital E. This one is capital E. Capital E is called Young's modulus or modulus of elasticity. Okay, so here this is our given diagram. Here this one is I consider this first cross section as a section 1. Okay, this is section 1. This is section 2. So A1 is the area of the section 1, A2 is the area of the section 2. Here the area is in mm square. Okay, so the stress also in mm. Okay, now the length. this is the original length of the bar 1, that is L1, and this is the L2. Okay, this is the original length of the bar 2. So L1 equal 90 mm, L2 equal 120 mm. L1 and L2 are the original lengths. Okay, by using these original lengths, you have to find out the change in length. That is delta L1 and delta L2. You have to find the value of delta L2. The total deformation is obtained from adding of these two values. Okay. Now the given data is tensile load is given. So the tensile load equal to, here the tensile load is equal to 160 to 10 power 3, because 160 kilonewtons is given. Okay, so here you can observe here 160 kilonewtons is the load acting on the bar. So 160 kilonewtons, 1 kilo equal to 10 power 3 newtons. So the total load acting on each bar equal to 160 kilonewtons, equal 160 to 10 power 3 newtons. Okay, and the length of the section 1, that is original length of the bar 1 equal to L1 equal to 90 mm, and area of the bar 1 equal to A1 equal to 50 mm square. Okay, both are in mm. And the length, original length of the bar 2, L2 equal to 120 mm, and the area of the bar 2 equal to, so the area of the bar 2 equal to 100 mm square. Okay, and L2 equal to 120 mm. Okay, and the Young's modulus capital E equal to 200 GPa. 1 GPa equal to 10 power 9 Pascal. Okay, and 10 power 6 Pascals equal to 1 Newton per mm square. Okay, so here I will explain. 1 here 1 Pascal equal to 1 Pascal equal to 1 Newton per meter square. Okay, Newton per meter square. 1 Newton per meter square equal 1 Pascal. Okay, 1 megapascal equal to 1 megapascal equal to 10 power 6 Newton per meter square. So 1 megapascal equal to 1 Newton per mm square. Okay, so 1 gigapascal equal to 10 power 9, 10 power 9 pascals, or 10 power 3 megapascals. Okay, so that's why 200 gigapascal equal to 210 power 3 Newton per mm square. Now already we have discussed about total elongation of the component. So from that formula, so delta L equal to total deformation or total change in length. Delta L equal to load acting on each bar by Young's modulus of the bar, Young's modulus of the bar material. Okay, into L1 by A1 plus L2 by A2 plus L3 by A3 plus L4 by A4. That is the formula for bars of varying cross sections. Okay, substitute the values of P, E, L1, L2, A1, A2. You will get the value of total change in length or total deformation in the bar equal to delta L equal to 2.4 mm. Okay, this is the formula for total change in length. In this problem, if you want to determine stresses induced in each bar, then you will use the formula sigma equal to load by area. So if you want to calculate stresses induced in each bar, then the formula for stress sigma 1 is the stress induced in the bar 1 equal to load acting on bar 1 by cross section area of the bar 1. This is the stress induced in the bar 1, and the formula for stress induced in the bar 2 equal to P by A2. P by A2 is the formula for stress induced in the second bar. Okay, so and delta change in bar 1, change in length in bar 1 equal to the formula for change in length equal to C P into L1, P into L1. L1 is the original length by A1, A1 into E. A1 into E is the formula for change in length in the bar 1, and similarly delta L2 equal to change in length in bar 2. In bar 2 equal to P into L2, L2 by A2, A2 into E. Okay, these are the formulas for stress and strains induced in the bar 1 and bar 2. Okay, now I am going to explain about another problem. So yeah, this is the problem. A compound bar ABC 1.5 meters long. Okay, here the total length of the bar is given, that is 1.5 meters. Is made up of two parts of aluminum and steel. Okay, this is the formula for this problem. This is the diagram for this problem. Here this is the one bar, that is it is made up of aluminum, and this downward bar is made up of steel. Okay, that cross section area of the aluminum bar, here the one condition is given, that is very important in our problem. The cross sectional area, cross sectional area of the aluminum bar is twice that of the steel bar. Okay, so here you can observe here the cross sectional area of the aluminum bar. This is the aluminum bar. This is the cross section area of the aluminum is A. I consider AA as aluminum and AS as steel. Okay, AS is the area of the steel bar. AA is the area of the aluminum. Okay, here the area of the aluminum is equal to uh, three times the two times the area of the steel. Okay, that means area of aluminum rod equal to twice that of the steel bar. That means two times the area of the steel, that A S 2 AS is the relation between areas. Okay, aa equal to 2 AS, and area of the aluminum rod, this rod aa aluminum, area of the aluminum is equal to two times the area of the steel. Okay, and the rod is subjected to axial tensile load. Here the load acting on each bar is 200 kilonewtons. This one is a tensile load, so you have to consider positive sign for tensile loads. And if the elongations of the aluminum and steel parts are equal, here one condition is there: the elongation of aluminum and steel parts are equal. That means uh, delta L for delta L for aluminum bar equal to delta L in steel bar. This is the condition for this line, meaning is delta L A equal to delta L as delta LA is the length of the aluminum bar, LS is the length of the steel bar. These are the original lengths, and delta LA is the change in length in aluminum bar. Delta LS is the change in length in steel bar. Here the condition is elongation or change in length of the aluminum and steel parts are equal. So you have to use this relation. Okay, you have to use this relation. By using this equation, you have to find out the original lengths. Okay, here the original lengths are not given. Okay, find the lengths of the two parts, that is LA. Here you have to find out LA, original length of the aluminum bar, and original length of the steel bar. You have to find out these two values. Okay, take Young's modulus for steel as 200 gigapascal, and E for aluminum as one third of the E steel. Here Young's modulus, that is capital E for steel is given, that is ES equal to 200 gigapascal. 200 gigapascal is given, but the Young's modulus for aluminum one third of steel. Okay, that means the Young's modulus for aluminum equal to 1 by third of steel, that is 200 by 3. 200 is the value of steel. Okay, 1 by third of steel. 1 by third of steel means uh, ES, Young's modulus for steel by 3, 1 by third. Okay, so these are the conditions in our problem. Okay, by using these conditions you have to find out the original lengths, that is length of aluminum bar and the length of a steel bar. You have to find out these two values. Okay. Okay, so these are the given values in our problem. Okay, capital L is the total length of the bar, that is capital L equal to 1.5 meters, and AA, here AA is the cross sectional area of the aluminum bar, but from our condition, from our given data, the area of the aluminum bar is called twice that of the steel bar. So by using this condition, area of the aluminum bar equal to 2 times the area of the steel. Okay, AS is the area of the steel and AA is the area of the aluminum. Okay, the load acting on each bar, that is P equal to 200 kilonewtons. 1 kilonewton equal 1000 newtons. So 200 into 10 power 3 newtons, that is the load acting on each bar. And the modulus of elasticity of steel is given, that is 200 gigapascal. 1 gigapascal equal 10 power 9 pascal, and 10 power, and also 1 gigapascal equal 10 power 3 megapascal. 10 power 3 megapascal. 1 megapascal to 1 newton per mm square. So the formula for 1 gigapascal equal to 10 power 3 newton per mm square. Okay, and here the Young's modulus for aluminum is equal to 1 by third of Young's modulus of steel. So Young's modulus of aluminum equal to 1 by third of Young's modulus of steel, that is ES by 3. So these are the given data. So by using these values you have to find out the original length of the aluminum part and the original length of the steel part. Okay, so already we know the formula for change in length. This is the formula for change in length. Change in length in aluminum bar equal to load acting on bar, length of the aluminum bar divided by cross sectional area of the aluminum bar into Young's modulus of the aluminum bar. Okay, this is the formula for change in length. So already we know the total load acting on each bar, that is P equal to 200 kilonewtons. So this is the value of P, 200 kilonewtons, into original length of the aluminum bar. The value of you have to find the value of LA. Okay, here LA is the original length of the aluminum bar. Okay, and here area of the aluminum bar is given. That value is 2 times the area of the steel bar. So use that relation 2 AS. Here AS also we don't know. Okay, and the Young's modulus for aluminum is given, that is 1 by third of the steel. So the Young's modulus for steel equal 200 gigapascal divided by 1 by 3. So here from this relation, the value change in length in aluminum bar is in relation, is in length of aluminum and area of the steel. Okay, this is the equation 1, and by using same formula for steel bar, Okay, change in length in steel bar equal to load acting on steel bar into length of the steel bar by area of the steel bar into Young's modulus for steel. Okay, substitute all these values. Here the length of the steel is not given, so and also area of the steel also not given. Okay, by using load P and Young's modulus, okay, you will get the answer LS by AS. Okay, here 200 into 10 power 3, 210 power both are cancelled. So LS by S is the value for change in length for steel. This is the equation 2. By using equation 1 and equation 2, here from given data already is given that the total elongation in the aluminum bar and steel bar both are same. Then we have to equating the equation 1 and 2. Then you will get the answers of original length of steel bar and original length of the aluminum bar. Okay, this is the equation 1, this is the equation 2. By equating these two equations, you will get the answer LS equal to 1.5 LA. This is the relation between two materials. Okay, this is a relation. By using this relation, the total length, already we know the total length, that is total length equal to length of a aluminum bar plus length of a steel bar. Okay, here the total length of the bar is given, that is 1.5 meters. 1.5 meters is given, that is 1.5 into 10 power 3 is given, that is equal to LA plus LS. Here the length of the aluminum bar is not given, and the length of the steel bar is obtained from above relation, that is 1.5 in 1.5 LA. Okay, so by here this one is also in LA, this one also in LA, that is the length of aluminum. So by using this equation, you will get the answer, that is the length of the aluminum bar equal to LA equal to 600 mm. This is the original length of the aluminum bar, that is 600 mm is the length. And after getting this length LA, okay, by using this equation, that is LS LS equal to the formula for LS equal to 1.5 LA. Okay, substitute the value of LA in this equation, you will get the answer, that is the length of the steel LS equal to 900 mm. So here you can observe here LA is the original length of the aluminum, LS is the original length of the steel. Okay, these both are the our required answers. Okay, okay friends, thank you. Okay, in next class I will explain more problems on these bars of airing cross sections. Okay.